All right. This mic is
All right.
way too tall.
This mic is way too tall for me.
All right. Well, very good. Now,
The reason why we came up with this title actually has to do with the fact that our Lunar Science Institute team called DREAM actually met with Mihai Harani's Colorado dust team. We started talking about a number of different topics that we have in common. We started talking about dust transport, and I can tell you the room completely polarized. People stood up and said there is no way dust can move off that surface, and other people were saying, oh, sure it does. We know it does. And I couldn't believe how polarized and different the points of view were. So what I'd like to do is I would actually like to sort of review the past observations, Apollo-era observations, and identify supporting pieces of information and contrary pieces of information that are associated with lunar dust transport. Now, I think we all have some kind of interest in lunar dust transport. You know, I have to say it didn't end up in the decadal study in Chapter 5. You don't see anything in there about lunar dust transport. It's really, you know, exploration's always seems to be more interested in it from a health hazard point of view. But to us in the science community, there's a basic interest in lunar dust, and that is it's a surface energizing process. I mean, certainly, if something is lofting material, possibly 30 kilometers into the atmosphere, you might want to know what's driving that process. I mean, it seems pretty clear. But the body of evidence to date is sometimes circumstantial, sometimes argumentative even, and anecdotal, as Rick Elphick mentioned earlier. And so, and the forces that move this dust have not yet been identified. And I think in the end, hopefully you'll realize that really the key is we need something like a LADI that will really help differentiate some of what we know and don't know. The observation that most people, that Rick Elphick talked about this a little bit, most people are familiar with is are the surveyor images of this low altitude horizon glow. Seen after sunset for a couple hours, this glow occurred a couple hundred meters away from the spacecraft. It's consistent with forward scattered light from dust that then scatters back into the surveyor cameras. The dust size is about 10 microns. Is kind of optimal for this kind of a thing. Oddly enough, though, that the mass flux associated with this is much larger than you would expect from a meteoric secondary ejecta kicked off the surface. So Criswell in '73 suggested that very large terminator electric fields might account for the lofting or the levitation of this dust. What we know now is that the fields may not be that large, primarily due to the fact that this region is immersed in a conducting plasma. The plasma will want to short out such large fields. But fortunately, laboratory data suggests that you can still get the dust lofted even at lower potentials. Now, how this supports lunar dust transport, the pro here in this case is that the pictures are tangible. They're right there. Clearly something is going on. The other very strong support was some work, analog work done in a lab by Mihai Harani's group, Sisyphus in all 2002, where they could actually get dust on the order of 10 microns or so levitated off of a table. This was in a plasma chamber with actually relatively low potentials. Very low potentials. They had to agitate the dust a little bit, which might be like, in some sense, almost analogous to an impact. But even at higher potentials, you could get the dust lifted and lofted. What you're seeing here are negative images of those lofted grains. I might point out that in this lab experiment, it wasn't a perfect reproduction. The heat fields were still higher than what you would expect on the moon, but they certainly weren't as high as Criswell suggested. So overall, this is, I think, a pretty strong, at least in terms of cases. This maybe is a relatively strong case with this beautiful analog study of Sisyphus. The second observation, which is actually highly controversial, is our dust focus group just recently met and had some interesting discussions about that, is the Lunar Ejecta and Meteorite experiment by Otto Berg, described in '76. Now really, this detector was designed to detect interplanetary dust, those dust grains that are moving at many tens of kilometers a second. And it may have gotten a few of those hits, but what was really interesting is around the terminators, around sunrise, in sunset, it detected a number of impulses, particularly on the front grid. And subsequent lab tests suggested these impulses could be triggered by fairly heavily charged grains moving slower and being induced in the front detector. One of the interesting points about this is on the at sunrise. Let me see it. Sunrise here, the dust seems to be flowing in the eastward direction, and at sunset, the dust seems to be flowing in the westward direction. So in both cases, it appears to be moving in an anti-sunward direction.
There's a reason why.
Now, there's a reason why.
There's a reason why.
There we go. There's a reason why we sort of like that, and that is because if the solar wind is flowing, you would expect that leeward edge of the Taurus littoral valley to become strongly negatively charged, and dust could be lofted or shot out from these negatively charged surfaces. So you might expect the sunward-facing detector that would detect the anti-sunward moving particles to peak up. And you can see here at sunrise, that's the east sensor. At sunset, it's the west sensor. You can kind of see there's some east sensor also kicks up as well. A couple downsides to this data set, though, is this system wasn't really designed to detect these slow grains. And the lab study suggests that there's a issue with the pulse height analysis circuit, where the circuit may have stayed on and kept, in some sense, made the duration of the event longer in the system than it really was. That may have created an ambiguity. Also, recently, there's, as many people may know, there's a recent paper by O'Brien talking about the possibility that EMI might be part of this as well. So this is a slightly more circumstantial data set, but in the context of the surveyor instrument, they are somewhat consistent. In other words, they're not inconsistent with each other. Well, if you think things are confusing at low altitude, at high altitude, you have this high altitude horizon glow that was really observed. Probably the most famous observations are the Cernan sketches on Apollo 17, where he was looking out the window and saw, and I think Rick Elphick showed these as well, saw this glow. Now the central part is the zodiacal light, but off to the sides are these streamers, but particularly off to the sides is this glow. It's the high altitude horizon glow that's believed to be, that could be accounted for by high altitude but very small dust particles. And some of this was captured actually, fortunately, in the Apollo cameras. And McCoy in '76 created a zeroth order model where he assumed the grains were 0.1 micron in size. That's pretty small grains. Lopped it to relatively high altitudes, so that at a kilometer you had like maybe half a grain, half a particle per cc, 0.01 particles per cc at 10 kilometers, and maybe 10 to the minus 5 grains per cc at 100 kilometers. So this high altitude dust is small stuff being shot way up.
Recently, this was
the camera light scattering from the camera was revisited by Dave Leonard. And actually, what Dave did is he actually reassessed and reanalyzed the zodiacal light curve and found that actually it probably should be up a little higher than the numbers that they were using back before. And when you actually put those numbers in, you find that at least in Apollo 17 and Apollo 15 sunrise, Apollo 17 sunset, you don't see much excess brightness, but in the Apollo 15 sunset, you see a lot of excess brightness. And when you convert that via Meade scattering code, you actually get slightly more conservative estimates for the dust. You may not get any scattering that's obvious above 30 kilometers, and at 1 kilometer, your values were lower than the original McCoy zero model, made by a factor of 5 to 8 or so. Now, supporting the pro to this, these observations, the anecdotal evidence that were provided in the sketches are supported by the camera, because the camera did see a glow, which is, I think, really good. So something is going on. Again, that's reassuring. The camera analysis, though, of course, you have to take into as Dave showed in his paper, have to take into account proper zodiacal light subtraction, and it's also very sensitive to the assumed particle size. One of the things Dave found is that if you assume that the particle size doubled, the concentration of grains actually dropped by about, to get that same brightness, actually dropped by a factor of 100. So it's a big exponential dial, if you will, on the particle size. The other thing that we don't know is we really have no idea how the dust could possibly get that high. Back in 2005 or so, electrostatic arguments were provided, but they really can't completely explain things fully. For example,
Tim
this
Stubbs,
paper by Tim Stubbs and all, I think I was a co-author on that.
Nice paper. Tim's a good guy.
Nice paper. Tim's a good guy.
What he suggested
that possibly some of these smaller grains get shot right up through the plasma sheath and get up to high altitudes, really being almost like a boomeranged up through the, or boomerang isn't the right word, but catapulted up to the up to high altitudes. Of course, what he found is when he did his model here is that on the day side the grains would maybe get up to 10 meters, 0.1 micron grains. The 0.1 micron grains on the night side and up at the terminator really only get about 4 kilometers. So they couldn't really get up to many tens of kilometers in altitude. They got up higher. Tim also assumed that the grains were charged at the plasma potential, which may be, which means that they were pretty liberally charged. And that helped them get pretty high.
More recently, a
nice paper by Andrew Poppy and Mihai Hrani, as part of their Lunar Science Institute work, found that these plasma sheaths themselves tend to be somewhat complicated. Like for example, on the day side, in the photoelectric sheath, you have electric fields that point outward, but you actually have a pretty large region of where the electric field points inward, and that's this very little bump right below here. I know this is not the greatest picture of it, but this is on a log plot. It's a very long region where the electric field points inward, and this in fact would retard dust motion. So the dust would get accelerated in this part of the electric field, but then get retarded in this part of the electric field, and as a consequence, it would really kind of squelch or push down all these grains, or not allow these grains to get nearly as high as you would think if you just had the first part of the sheath. As Andrew suggested, grains on the order of a tenth of a micron, 100 nanometers or so, really only get to heights less than 10 meters or so. In this, he also assumed that the grains were only charged with one elementary charge. Now, I will tell you that this brings up a whole nother issue that Mihai Hrani has talked about and Chris Gertz talked about in his review, and that is the issue of Duff's surface charging. It's really a dilemma. And let me explain this dilemma. I'm almost wondering if this is too much detail, but this is such an interesting calculation that you have to go through it. If you assume that you have E fields that are typical of a sheath, about 10 volts per meter, and you apply Gauss's law, the same law you learn in Physics 1, for the surface charge, this is surface charge, sigma is the surface charge, what you find is the surface charge density is about, for a 10 volt per meter field, is about 10 to the minus 10 coulombs per meter squared. But if you then ask yourself, in a 1 micron by micron area, how much charge is held, it's 10 to the minus 22 coulombs. In other words, a 1 micron grain in a typical sheath situation should only possess about 1/1000th of an elementary charge. Now, if that's the case, how do these grains at micron scale or smaller get shot off the surface? In fact, what it suggests at a statistical level that maybe only a few grains, like 1 in a million or 1 in a billion or 1 in a trillion, we don't know that number, get released in this plasma charging process. Now, of course, this assumes it's a smooth surface. If you have a rough surface, you could have unusual surface capacitances and obviously concentrations of electric field, but it still doesn't suggest that every grain would move. Now, remember, the Sisyphus experiment got the larger grains to move, but the electric fields were pretty large, and the grains typically should have had about 10 to 20 elementary charges on them. But the small stuff, really tough to lift off, and I think Rick mentioned this as well in his talk about LADI. So this brings up then that this is where we started talking a little bit to the geologists, and the geologists said to us, hey, if there's all this electrostatic transport, where's the geological evidence for it? Tycho craters rays. They've been there for 100 million years. If dust is electrostatically moving around like you guys are talking about, why are these rays still there? And that's a good question. Maybe it goes back to this idea that maybe only 1 in a million, 1 in a billion, 1 in a trillion, again, a number we don't know, those very few grains move, and it's not all of them that are moving. But this talking about crater rays actually segues into a second process that can transport dust, and that is impactors. They are an obvious transport mechanism. These rays that extend hundreds of kilometers are themselves associated with a transport process. And we know that there are impacts of micrometeoroids continually lofting mass at the moon at the tens of microns sort of scale, moving mass around. So it may make sense that impacts are a possible lofting mechanism. And what I show here is some evidence in the geological side of the house from Wentworth and all, where Apollo 12 ropey glasses were thought to be of an exotic origin, possibly from Copernicus crater. And here are the Copernicus crater rays. That's Landsberg crater. Here are the Copernicus crater rays that kind of hit near the Apollo 12 landing site. So it's thought that maybe some of this ropey glass came from someplace else, kind of consistent with this idea. But probably the most stunning evidence visually is of secondary impact ejecta. It comes from the Stereo spacecraft, where interplanetary dust, when these high-speed micrometeorites hit the thermal blanket, and the cameras caught this. This camera is designed to look at the sun. This camera is designed to actually look at competent scattering in the solar wind, and you can just see all kinds of debris that comes off of this dust hit. So you can imagine the moon may be undergoing a similar kind of thing when dust hits, though the thermal blanket is actually a little bit more flimsy, from what I understand, than lunar regolith. But again, the surface of the moon is covered, but it gets hit by this dust all the time. So, but here's the case against secondary impact ejecta, and that is, you look back at the surface images from Surveyor, and it was concluded that this glow was simply too bright, and also quite localized as well to the terminator region, that the secondary impact ejecta simply cannot explain the intensity of this glow. Of course, it's not clear that secondary impact ejecta can explain the high altitude glow as well. There's been some discussion about it. I think in the Glennar paper that just came, it's about to be released in Planetary in Space Sciences, they talk about maybe a saltation effect, but no one's really connected secondary impact ejecta to the high altitude glow, which means that we really need LADEE now more than ever. In fact, LADEE's going to have two dedicated, two dust experiments, the lunar dust experiment, which is an in situ detector that works on impact ionization processes up at, and also there's going to be the UV spectrometer will also be able to remote sense dust, looking at a column across the moon. And what I show here are some modeling results from Dave Glenard and Dennis Richard, showing how a dust grain of a few fractions of a micron would appear in the. This is actually a set of dust grains in the UVS, and you can see that it should be able to detect this kind of activity if you use like a McCoy zero model, for example. What's interesting about LADEE, it'll be up during solar maximum. So during a solar storm, if the surface charge suddenly increases and you start seeing a heavier dust load, that might favor electrostatic lofting as a mechanism. LADEE will be also up during meteor streams when the moon passes through meteor showers. And I think Rick Elphick has a nice plot where there's 2 or 3 or 4 showers that clearly pass through. If we start seeing dust levels increase there, that again might favor an impactors as a driver. Who knows? You might see it in both cases. And of course, as Rick showed earlier, that there's some really interesting observations from LRO LAMP that maybe they're seeing something off at the horizon. Whether it's true horizon glow or not, I think is still being examined. So in conclusion, last night when I woke up in the middle of the night and I said, this poor audience, I cannot connect the low altitude horizon glow to the high altitude horizon glow. I can't come up with a single mechanism that can explain both observations. I mean, what are they going to think? This is like a terrible talk. And I thought, no, wait. That's why we got LADEE. That's why LADEE's going to help us solve some of these problems. So then I could go back to sleep. I still feel sorry for you as an audience, but because you still had to kind of suffer through some of this. But in fact, part of the problem is that the observations to date have not been systematic. They've been and have not been with an instrument that's been really designed to look for dust. And LADEE certainly is going to help out. And certainly in the future, a great ideal situation is to have a surface dusty plasma package along with orbital assets. So you can actually kind of try to make the connection from low altitudes to high altitudes. And again, even though it wasn't in the decadal, even though lunar dust wasn't mentioned, I think it's still important because it's a basic process. Again, if you're off and dust up to 30 kilometers, you might want to know the process that's doing that. And that's pretty much it. I think I'm pretty much on time. Okay, all right, good. Clive.
Just a question with regards to your electric sleep surface measurements give you more information? Would surface measurements give you more information?
No, actually, surface measurements would be great because you're right there where it's happened. So if it's surface charging and there's a change in surface charge and you see the dust lift, that would be awesome. In fact, some of these surface packages that were flown were, themselves really good, but it would have been great to have sort of a complementary measurements right nearby. Like if you have a dust detector, maybe electric field sensor, maybe an interplanetary dust detection system to look at increases if you're in a meteor shower, maybe even a surface UV instrument to go with a UV instrument in flight. Of course, this is like asking the butcher how his meat is, I mean, of course I would want that. I don't know if anyone would ever pay for all that, but but yes, I have a long shopping list of what could be landed on that would be great to put on the surface to solve this kind of problem. Yep. Yes and no. I mean, I'm sure you could come up with something that might detect dust. The problem that you have, which is the same problem you have here, it's a contextual problem. So you really need almost background instruments to help you figure out what's going on with the environment. So if you could do, and some of that's, like a Langmuir probe or a DCE field system, I mean, that's really not COTS. Now it's getting into, expensive gear. Now, that's not to say that if, someone willing to, provide an opportunity, people could find a way to do it. I would never underestimate the capabilities of PIs in this room to come up with a scenario to make something work and get as much as you can out of nothing.
Sure, I'm from the University of Colorado. I just have a comment on the surface charging. From the data from our lab and from the lab in Iowa showed the charge on single particle can be much larger than the calculation from the Gauss's law.
Yep, and I agree with that. In fact, yeah, and there are a lot of strange, and I almost call them hidden capacitances. As soon as things get rough, you actually can, in some sense, duck dipoles. And in fact, near a surface, it might be that you have a grain fully charged, but then as you bring it down towards the surface, you actually get an image charge coming up, and so the monopole is reduced, and you get a dipole, and in effect, you've sort of negated the fact the charge on the original grain. Yeah, but so yeah, I can believe that experimental values are larger than. I think
that can significantly increase the chance to lift off the dust particles.
Right. Absolutely.
Just to comment on LADI and what it'll do for lower altitude dust that Clive was asking about. The ultraviolet invisible spectrometer will be doing limb scans right down to the very limb of the moon. And so getting down to altitudes, from LADI orbit of just a few kilometers and be able to make measurements of the dust there. It's also making measurements of extinction, very, very challenging measurement, but of solar extinction measurements as LADI goes behind the moon. And then secondly, LDEX in situ dust measurements will be taken down to the very minimum altitudes that LADI will fly over the morning terminator down to 20 to 25 kilometers.
That's awesome. Altitude. Yep, that's good. See, and this is, going in, the other observations were more, hit and miss. They happen to catch it on camera, they draw a sketch. I mean, having a plan beforehand is good. You can quote me on that. Having a plan beforehand is good. It's like I should be at Farber College, knowledge is good. Faber College, thank you. I stand correct. Well, there.